The introduction of components allows us to deal with vector operations now in a real, explicit, mathematical, algebraic kind of way. So for example, let's illustrate this in 2 dimensions. Let's take two-dimensional vectors, A and B, and add them together. Remember, when we add, we take A and then we put B's initial point at the tail, or the terminal point of A, and draw it up there. And then if we start at A and end at B, that gives us A plus B. Well, we can see pretty explicitly that the x component of A plus B is the x component of A plus the x component of B, this whole length right here. Similarly, the y component of A plus the y component of B gives the y component of A plus B. So the components of A plus B are just the sums of the components of A and B. A1 plus B1, A2 plus B2. This generalizes nicely to 3 dimensions. The sum of A and B is just the sum of their components. A1 plus B1, A2 plus B2, A3 plus B3. Now let's take scalar multiplication. Here I'm taking a scalar C and I'm assuming that it's positive and bigger than 1. So the effect is that it actually stretches out the vector A. But it stretches it out equally in both directions. Multiplying by a scalar doesn't change the direction of the vector. So since we're, so this is what the vector CA looks like. Going the same direction. I'm drawing them both starting at the origin, so they're going to lie in the same line. Just CA is now a little bit longer because I'm assuming C is bigger than 1. What does it do to the components? Since they lie on the same line, both of the components have to be multiplied by the same number C also. So CA has components CA1, CA2. This extends to 3 dimensions as well. C times A, it has components CA1, CA2, CA3. And even though I sort of waved my hands about this being a number C which is bigger than 1, it works for any scalar value of C. Okay, so let's do an example. Let's let A be the vector 1, 3, negative 2, and let B have components 0, 4, and 3. Let's find a couple of different things. So negative 3 times A. Well, negative 3 times A will have components negative 3 times 1, comma negative 3 times 3, comma negative 3 times negative 2. So this works out to negative 3, negative 9, and 6. That is negative 3A. Now we want A minus B. Well, let's just remember that the difference of B from A is really adding the negative of B to A. And the negative of B we can obtain just by negating its coefficients, because it's just negative 1 times B. So this is really going to be 1, 3, negative 2 minus, plus the negative of B, which is 0, negative 4, negative 3. This ends up being 1 plus 0, 3 plus negative 4, which is just 3 minus 4, and negative 2 plus negative 3, which is negative 2 minus 3. So at the end of the day, all this really shows is that when I subtract 2 vectors, I just take the difference of their components. I could even put a minus here. So 1 minus 0, 3 minus 4, and negative 2 minus 3. And this works out to 1, negative 1, negative 5. Finally, let's do this last one. 2A plus 3B. I'm going to do this a little bit. First of all, I'm huge, so I've got to kneel down. I'm going to do this a little bit faster. Okay, I'm still up here. So 2 times A gives me 2, 6, negative 4, plus 3 times B gives me 0, 12, 9. When I add those together, I get 2 plus 0 is 2, 6 plus 12 is 18, negative 4 plus 9 is 5. Great. So that is that vector. So vectors are really a new algebraic object to us, and these operations on them, although we're calling them plus and multiplication, addition and multiplication, we really need to be careful that they actually do satisfy the algebraic properties that we expect. And pretty much because vectors can be represented by components and addition and multiplication by scalars work pretty much component-wise. That means that all the properties that real numbers satisfy in terms of algebra, at least a lot of them, carry over to vectors. So for example, vector addition is commutative. It is also associative. Doesn't matter which order you add things in. When you add three things, do I add the first two first, the second two first? Doesn't matter. When you add the zero vector to any vector, you get the same vector, so that's the additive identity. And any vector plus its negative is equal to the zero vector. So that just says that everybody has an additive inverse. Also, scalar multiplication distributes over vector addition. And also, it distributes over plain old regular addition of scalars, which is just real number addition. Scalar multiplication is associative with regular multiplication. I can multiply the scalars first and then multiply against the vector, or I can multiply one scalar against a vector and then the other scalar against the resulting vector. Finally, 1 is the multiplicative identity when it comes to scalar multiplication. Again, though, we don't have any multiplication of two vectors going on right here, and when we introduce that to the mix, that's where these familiar algebraic properties are going to fly out the window, so we do need to be careful. Now, oftentimes we will represent, and this happens a lot in, I think, physics and engineering, vectors are, instead of being written out in terms of component, are written out in terms of the standard basis vectors, I, j, and k. When I first learned to write them, I learned to write hats over them, and that just sort of is how I write them. But you can put a vector over it, sort of the vector sign over it, or you can write them out in bold. So I is the standard basis vector in the x direction. It's 1 in the x direction and 0 and 0 in the other two. J is the standard basis vector in the y direction, 1 in the y direction, 0 in the others. K is the same thing for the z direction. So here's I, just going up 1 along the x-axis, J just going up 1 along the y-axis, and K just goes up 1 along the z-axis. So this just gives us another way of representing vectors. So these standard basis vectors give us another way of writing out vectors. If A is the vector with components a1, a2, a3, then let's consider the following vector. The scalar a1 times I plus a2 times j plus a3 times k. What is this equal to? Well, I is 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. So if a1 times 1, 0, 0, which is a1, 0, 0, a2 times 0, 1, 0, which is 0, a2, 0, and a3 times 0, 0, 1, which is 0, 0, a3. Adding them together, there's only one non-zero component for each of x, y, and z. a1 plus 0 is a1, 0, a2, 0 is a2, 0, 0, a3 gives me a3. That's just a. So this is just a fancy way of writing out a. We'll find that this is actually kind of useful in some of our computations. Right now, it might seem a little bit silly. Just to give you a little bit of practice working with this, let's do this for question 2. If a is 2i plus 3j and b is negative I plus 2j, express a plus 2b in terms of I, j, and k. That means write it out like this, not in terms of components, like this, but in terms of I, j, and k, like